Alright, let's wrap up this discussion on types of loads with our final load, earthquake, also referred to as seismic loads. Earlier I mentioned that wind and seismic loads, despite both being lateral loads, are fundamentally very different. This is because wind is an external pressure or force acting directly on a building. Seismic activity, on the other hand, is an acceleration of the ground caused by the movement of tectonic plates. This movement travels in waves through the crust of the earth and causes a building to sway, and this swaying motion translates into forces due to the building's own weight and inertia. Inertia, in simple terms, is resistance to movement. If the building had no inertia, then it would simply fall over when the ground accelerates underneath it, and there would be no forces to design for. Consider these two scenarios. First, the case of a car crash between a drunk driver and a sober driver. Often in these instances, the sober driver actually sustains far worse injuries than the drunk driver. This is because the sober driver is alert and their bodies will brace for the impact. Their muscles tighten, increasing the resistance to movement, their inertia, and when their body suddenly decelerates, this may result in strains and fractures. Similarly, if you imagine holding up a cylinder with very little stiffness, for example, let's call this a pool noodle, and you wave it around, the noodle will flop back and forth and you will feel very little force in your hand. Conversely, if you take a more rigid cylinder, let's say that this is a piece of PVC pipe, with the same weight as the pool noodle, and you wave it around, you will feel much greater force in your hand as that pipe resists the movement. So let's keep that in mind as we move forward. Seismic forces occur in a building because the building has weight and inertia. Similar to our discussion with wind, we will first lay out the parameters that control earthquake load. Also similar to wind, we start with location. Different locations will have different ground accelerations depending on their proximity to fault lines that form between tectonic plates. For example, California has much higher seismic activity than Massachusetts. It's important to note, however, that buildings in both locations must be designed for earthquake forces. Just because we don't often feel earthquakes in Massachusetts doesn't mean that they don't regularly occur. Although they are relatively small, they can still impact buildings, especially old, brittle buildings that may not have been designed specifically for seismic loads. So seismic design is always required. Seismic detailing, however, is not always required, and we'll get into that more later. Next we have soil conditions. Seismic waves travel through the crust of the earth and through the upper layers of soil that most buildings are built on. These upper layers can vary drastically in their contents. We'll get more into that later when we discuss foundations. For now, consider these two conditions: a site with very hard, dense rock, or a site with soft clay or sand. Which do you think would have greater seismic forces? Next, as we had with wind loads, we have building size and geometry. Geometry plays a key role here with the code, as we will see in just a moment. The fourth parameter, as with wind, is the structural system itself. But the answer to our question here is a bit more complicated, as we'll soon see. Lastly, we have the weight of the building and damping. And as we'll soon see, it's not just the magnitude of the weight itself that matters, but also where the weight is distributed throughout the building. Now, let's look deeper into each of these parameters, starting with ground acceleration. As with wind loads, we have maps provided for us in the IBC for parameters that tell us the maximum ground acceleration to consider. And according to the code, these ground accelerations are based on a maximum considered earthquake, which is based on a targeted risk of collapse equal to 1% in 50 years. So there is a 1% chance every 50 years that a building designed to withstand these ground accelerations may collapse. In reality, the chances are probably much lower than that once you consider all the other factors of safety that are involved in the design of a structure. What we should note with this map is the areas with closely packed lines. Of course, everything on the west coast here is the obvious place that your eye will be drawn to. But there are also somewhat unexpected areas as well on the east coast. These areas are where engineers need to pay particularly close attention to seismic design and detailing of their structures. Moving along to soil conditions. ASCE 7 defines 5 site classifications based on the soil present at the site, and these site classifications are typically determined by a geotechnical engineer through testing. There are a variety of testing methods that a geotechnical engineer can use to classify a site, each with a different level of accuracy and cost. Keep in mind that a higher upfront cost for a more accurate test could end up saving the owner money in the long run, as the geotech may be able to assign a better site classification for the structural engineer to use. This could result in a much more simplified, economical structure. So let's take a look at these classifications. Basically, what you'll notice here is that the soil conditions become softer as we move down the line from A to F. And with softer soils, we have this phenomena known as wave amplification. Basically, when an earthquake occurs in the bedrock and the wave travels up into the upper layers of sediment, it refracts as it reaches the softer soils, and this refraction leads to larger magnitude waves. Imagine taking 2 buckets and filling one with dirt and the other you fill with jello. You place a little toy house in the middle of both buckets, and then you smack the sides of the buckets with your hands. The house and the bucket of dirt will likely not move at all, whereas the jello will send a much larger shockwave through your toy building. So imagine your soil like a layer of jello. The softer it gets, the worse your seismic forces become. Next up, building size and geometry. Let's first consider a wall with an elevation like this. When the ground shakes, the bottom half of this wall will not likely move very much at all. It has a large amount of inertia and it's located close to the ground. This skinny, tall portion, however, will have much more movement. Thus we will have a condition of concentrated stress at this corner, where these two pieces meet. This and several other building shapes and layouts are collectively known as seismic irregularities. Irregularities is a term used in code because everything that's not a box is irregular to the code. But in real life, some of these irregularities are quite common. So it's important to note that though there are ramifications for designing a building with these irregularities, it can be done. It just comes at a cost. So before we jump into these seismic irregularities, let's talk about our structural system. When we started our discussion on types of loads, we broke them into 2 main categories: gravity loads and lateral loads. And the reason we did that is because we designed the superstructure of a building with both a gravity system and a lateral system. Our gravity system, as we talked about last week, is made up of the deck, beams, girders, columns, and lastly the foundation. Many of the same components in the gravity system may also appear in our lateral system. For example, the deck, as we mentioned in week 1, is also the building's diaphragm, which is part of the lateral system. Some of our gravity beams, girders, columns, and parts of the foundation can also be included in the building's lateral system. In general, there are 3 main types of lateral force resisting systems that we will cover in this course. We've already mentioned at least 2 of them, and we'll cover all three in greater detail later in this course. The first is a moment frame. Next, we have a braced frame. And finally, we have a shear wall. These are the three main types of systems structural engineers design to resist lateral loads, and the placement of these elements in the building is key to the behavior and performance of the building, as we will soon see. So, our irregularities are broken down into plan irregularities and vertical irregularities. Let's start with the plan irregularities. And the first one is called torsional irregularity. This irregularity occurs when we group all of our lateral system elements to one side or one corner of a building. When an earthquake occurs, the sum force that is generated by the ground's motion acts through the center of mass at each floor level. The lateral system counteracts this force with a reaction that occurs at the center of rigidity. This creates a moment arm, which creates twisting in the building. In simpler terms, if you imagine this floor plan as a piece of paper, and you place a finger at the center of these lateral elements here, and then you take your other finger and push upward on the paper here, the paper will twist around your first finger. That twisting motion causes additional stresses in the building that must be accounted for. Next, we have reentrant corners. With wind design, we were concerned about exterior corners becoming too sharp. Now with seismic design, we are concerned with interior corners, or reentrant corners. So basically, never design a building with corners, I guess. I'm kidding, of course. Next, we have discontinuous diaphragm. We will talk more about diaphragm behavior later, but for now, just know that placing a big hole in the floor at one level impacts the lateral system's behavior and can add cost to the structural system. Next, we have out-of-plane offsets. This is when a lateral force resisting element, say a shear wall, is displaced in plan from one floor to the next. And you can see that in 3D here. Similarly, if we displace the element from one floor to the next, and also realign that element, we would have a non-parallel offset. The Massart Treehouse Residence Hall was actually designed with this seismic irregularity. Along the exterior of the building, here, this face of the building, there is a moment frame hidden behind these lovely architectural panels. This moment frame is parallel with the face of the building, but then it steps back in plan where the building also steps back, and follows the curved exterior of the building down here. This is because of a large sewer easement underneath the ground in front of the building. So the footprint for the building had to be kept to this size. That means that at this level here, we are not only transferring gravity loads, but also lateral loads across this cantilever. Or if we look at that a little more closely, here at this level, we are transferring our lateral system and our gravity system from this line to this line. Thanks to some very clever engineering, the team was able to achieve this very unique and beautiful building while also keeping away from the sewer easement underneath the ground. So that covers all of our plan irregularities, and in the next video we will be discussing vertical irregularities and the remaining parameters that control seismic loading.